Okay, let's take a break from parallel lines and let's talk about perpendicular lines today. So if you remember, perpendicular lines are two lines that intersect to create a right angle. Say they look something like this. So we can have, for example, line A and line B. And remember, these could also be line segments. And as long as you know they are intersecting to make this right angle, then we can say that these lines are perpendicular. And the sign for perpendicular is this upside down T. So again, this means perpendicular. Okay, so a couple of things we're going to do with our perpendicular lines. We're going to have a few theorems we're going to look at later on. But first, let's talk about what we call a distance from a point to a line. And there's lots of distances you can calculate from a point to a line, but here we're going to talk about the shortest. So when I'm asking you to find the distance in this diagram, in this section, we're going to be looking at the shortest distance. And that shortest distance is going to be the perpendicular distance from the point to the line or line segment. So let's go ahead and write that down. All right, so again, we're defining the distance as the perpendicular distance from a point to a line or a line segment. So if you look at this example below, I have point B and line L. And you're probably thinking, well, if you want me to find the distance, what are you talking about? Because I can draw a line. Oops, here we go. I could draw a line here, right? I can draw a distance here. I can draw a distance anywhere, all over the place, right? But so it's really unclear, so we need that definition. So if we look at that definition, we're looking at the perpendicular distance. So the actual distance I'm going to have you measure or calculate would be this one right here. So this is this distance we are talking about. This is going to be your shortest segment. So again, just to be really clear, unless I'm asking you for a specific segment length, so if I had like BA and A is way out here, and ask you to find that, so unless I tell you to find that specific segment, I'm asking you for the shortest distance. So we usually think human nature, we want to find the shortest distance from one point to the next. So here our shortest distance is going to be the perpendicular segment. Okay, so let's take a look at example 1. And two questions here. A, what is the shortest segment from A to line CB? So here all I'm asking you to do is name it. So if you take a look at the diagram, you might think, well, how do I know what's the shortest segment? So remember, when you're saying shortest segment, you should automatically be thinking perpendicular segment. So that's right now in my mind. So sorry, this should say segment. Make that a little clearer. So look at the diagram. What is perpendicular? Look for the right angle. And I'm going to see this perpendicular segment right over here, AP. So that means the answer to this question is AP, right? And that's perpendicular, or it's the shortest because it's perpendicular. So I'm just going to write that in parentheses so you can remember that, right? Shortest because it's perpendicular, right? From the point to the line, okay? So now the question is, well, what do you mean by solve for x? Take a look at B. X is right over here. We have this x plus 9, right? How does that factor into what we're doing? So remember, our shortest segment is AP. So no matter what, AP is the smallest in measure. So if you look at this x plus 9, that's CA, this segment right here, doesn't matter what it is, it's going to be bigger than than PA. So you can write an inequality. So no matter what, AP is going to be the smallest, so it's going to be less than x plus 9, okay? Oh, sorry, let's use notation here. So it's going to be less than CA, that measurement, and then substitute, okay? 12 is going to be less than x plus 9. Then use your algebra, subtract 9 from both sides, and we are going to see that x is greater than 3. And I don't care if you write this as 3 is less than x or x is greater than 3, they mean the same thing. It's up to you and how you want to write that order. Okay. But again, this is a little tricky. We're not writing an equation. It's going to be an inequality because that side, CA or AC, is not going to be the same length or even smaller than AP. So we want to use the inequality sign to create the problem. Okay. Let's take a look at some perpendicular line theorems to help us figure out what to do when we're looking to prove something's perpendicular or if we're given some information about perpendicular lines. So let's go ahead and look at the first one. Okay, so this first theorem, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So if you look at the hypothesis in this conditional statement, there's two things that we need to happen. We need to have a linear pair and they need to be congruent angles. So if you're given this, then we can conclude that the lines are perpendicular. So take a look at the diagram. This would be what you're given. So you should see two things happening. One, angle 1 and angle 2 are a linear pair. And you'll also notice from the notation here, angle 1 is congruent to angle 2. So if we have this information, we can conclude and jump straight to it and say L is perpendicular to M. And this is a super simple theorem to prove. All you have to do is remember a linear pair is supplementary, so they add up to 1 under 80. And since these two angles 1 and 2 are congruent, they've got to be 90. And by definition, a perpendicular, L and M would be perpendicular since perpendicular lines intersect at 90-degree angles. So that's our first theorem. All right, let's go ahead now and take a look at the second one. So theorem number 2, in a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other. So look at the key information in this statement as well. So our transversal is perpendicular to one line, and these lines have to be parallel. So we've got to be perpendicular to one, and then the two lines that we're looking at have to be parallel. If that's true, then that transversal is perpendicular to the other line. Okay, so let's take a look at the diagram and you can see what I'm talking about here. So this is what you'd have to be given right here. We need to be given two things, that the transversal A is perpendicular to one of those parallel lines. So A is perpendicular to B here by definition because we see that right angle at that intersection. And we also need to know that B is perpendicular or parallel to C. So if we have that information, then we can go ahead and say, well, then A should also be perpendicular to C. And that's a super easy one to look at because you can use your corresponding angles postulate, right? If this is a right angle right here, then down here it's also a right angle, and by definition, we've got perpendicular. So super easy to prove. Okay, one more, and we'll do one example. So theorem number 3 today. This third theorem is pretty much the converse of that second one. So now we're saying, well, if I don't know the two lines are parallel, but I know two coplanar lines are perpendicular to the same line, then I can say those coplanar lines are parallel to each other. And you'll see this just works because of the converse of the corresponding angles postulate. And that's a great way to prove this. So again, you're given certain pieces of information. So you need to know we've got two lines that are perpendicular to the same line. So, right, two lines perpendicular to the same line, right? So we've got to have that for sure. If we have that, then we know the lines are parallel. So basically, you should have a transversal that's perpendicular to two, at least two of the lines it's intersecting. If that's true, then those intersected lines are parallel. So again, the converse of what we just looked at in the second theorem. So you have to be given two things here, right? X is perpendicular to Z in the diagram, and I just drew it a little differently so you guys can see we're not always going to look at them in a horizontal or vertical position. It can be shown in any way. Just look for the key pieces. So we see that X is perpendicular to Z by definition. Again, see this right angle. That's the key thing we're looking for. Then we'll also notice that right angle for Y and Z. So that also tells us Y is perpendicular to Z. So if we have these two pieces of information, then I can say that x should be parallel to y. And that's because, again, of the converse of the corresponding angles postulate. And that's a great way to prove this theorem. So notice this time you're going to need two pieces of information to use any of these theorems. Make sure you're checking off kind of like a mental checklist. Do I have both pieces? If so, then I can make a conclusion.